Welcome everyone. So we're going to be talking about today our acids and bases. So this is basically a unit about the way that substances exist in nature, and some will release hydrogen ions, some will actually absorb hydrogen ions, and it really affects everything, including our own personal lives. And so if this adjustment isn't correct, it can actually cause death. And so your blood pH actually needs to be within a particular range as well. And so it's the effect of everything in our everyday lives, or the way that acids and bases end up playing out. Now, some acids and bases that we have in our everyday lives too, we've got something like bleach, we've got vinegar, we've got ammonia, and then there are things like citric acid, ascorbic acid that you've heard of. So we'll talk about some of those as well. This is sodium bicarbonate. We'll talk about that one too. Now, bases, acids and bases have a couple of different definitions, and so we'll also talk about those three different definitions. So there are Lewis acids and bases. We don't really talk too much about, even at the AP level. There are what are called Bronsted-Lowry acids and bases, and what you're used to are called Arrhenius acids and bases. And Arrhenius acids and bases basically just say that acids donate what? Acids release what when they're in solution? H plus, and bases release OH minus. Okay, so that's a basic acid-base definition would be the Arrhenius one. And so we'll talk about the other definitions as well, which are not very much different. Okay, so what we're going to start with here is we're going to actually take a look here at this is pH paper, and you can use different types of indicators in order to figure out if you have an acid or a base. And so very simply, we have acids are below a pH of 7 and bases are above a pH of 7. It's easy to remember because A comes before B in the alphabet, so that's easy enough. And at 7, we just say that the substance would be neutral. Okay, and so in other words, the amount of hydroxide and hydrogen ions that are in the solution should be equal. And we'll talk about what we mean by a melt. So we'll talk about that later on as well. So what you would do on this simulation, this is litmus paper, and so you can take this out and you can drop this into one of the solutions and you can check to see how it changes the color. And so here I would kind of line it up with the colors over here to figure out, and this is lemon juice. I don't know, it's kind of hard to see what this color, if it looks like it might be like a 2 or a 1 or something like that, or maybe a 3. And so you could line it up to figure out what the pH is. Oven cleaner, a lot of the cleaners that we use are, anybody want to guess, acidic or basic? Basic, very good. And so if I took oven cleaner, which is solution 2, and we check to see what something like that looks like, we can see it's in like the blue range, and so that lines up kind of around like the 12 or the 13 range. Seawater, anybody want to guess? Acidic or basic? Acidic, you would think a little bit more acidic. If we take a look at this, let's check and see. I believe it should be around a 9 or something like that. This is around an 8-ish. So typically they'll say that seawater is around an 8.6, something like that. Soft drinks, what about soft drinks? Acidic, good. And you've heard like phosphoric acid, you see right on the label that it'll say like carbonic acid. So if we dip this into solution number 4, we can see that this is more of like an orange color, so somewhere around like the 2 or the 3 range again. Pure water. What should pure water be? Yeah, that should be right at neutral. So as long as you have pure water, then it's, this is nothing else inside of it, then it should be a pH of 7. And antacids. An antacid is like an anti-acid, which probably should be basic. So if we take a look at the solution here, we can see again that this is in like the blue range, somewhere around like a 10 or an 11. Okay. All right, so acids and bases play a central role in the chemistry that affects our daily lives. Our bodies need acids and bases to function properly. A slight deviation can cause serious illness or death. Acids and bases are also important to manufacturing. Sulfuric acid, for example, is used to make fertilizer, steel, polymers, and other materials. Okay, so citrus fruits like lemon juice have a pH around a 2.2. Sodas, which we said were like phosphoric acid or carbonic acid, so you can get something like H2CO3 or H3PO4 would be some of the acids. Tomatoes have what is called ascorbic acid, and ascorbic acid is the formula is C6H8O7 for ascorbic acid. And so it doesn't really look like an acid, but as long as it's going to donate hydrogen ions, then that's what makes it an acid. In tea, they have what is called tannic acid. Okay, we all know vinegar. Vinegar starts with an A, acetic acid. Good. So we'll just write the formula for it. You can write HC2H3O2, but I want you to write it as CH3COOH. I want you to write it this way instead. And so that hydrogen right there, so this is not hydroxide, and that's tricky, okay? Because typically people will look at this and go, yep, that's a base. That is not a base. This hydrogen right here is your acidic hydrogen at the end, okay? So if you see the COOH group, that is specifically going to be an acid called, and you'll have propanoic acid and ethanoic acid, so carboxylic acids are what they're called. And so that's the way that they write those. Electrolytes, like in a car battery. And so does anybody know what type of acid is in a car battery? They mentioned it up here. Up here. Sulfuric acid. So like H2SO4, for example. Okay, bases. So mortar, they'll use calcium hydroxide, for example, and they will call this slaked lime. You'll see that they'll use slaked lime is what they'll call that. Antacid tablets. Does anybody remember? You can use sodium. Anybody want to guess? Not hydroxide. They'll use sodium bicarbonate. What is bicarbonate? HCO3. Now, that doesn't look like a base. But what happens is, as long as it's something that can attract hydrogen ions, that can pull up hydrogen ions from solutions, which when this splits up in solution, it'll actually grab another hydrogen. And so then you're thinking, oh, but then it looks like it's making an acid out of it. But what it does is then it forms, does anybody remember? H2CO3 doesn't stay as H2CO3. What does it actually turn into? H2O and CO2. Awesome. And so that's why you'll also sometimes start to burp too if you take an antacid tablet. Okay, and then household cleaning agents, like we said, bleach. Bleach has sodium hypochlorite. Do you remember what hypochlorite is? ClO, perfect. And ammonia, like the bottle of ammonia that you're seeing here, that's not actually, the formula would be NH3 for ammonia, but what do we know about NH3 at room temperature? It actually exists as a gas. So it's, our household ammonia is really NH4OH. It's actually ammonium hydroxide is what they use as ammonia. Acids and bases will react together, and I don't know if any of you remember this, but I talk about these two guys that are going into a deli, and they're going to sit down and they're going to have some like matzo ball soup, and their names are Walter and Saul. Good. Okay. So they form water and salt. And so I say Walter and Saul. Okay. And something to remember is do as you oughta, add the acid to the water. Good. Always add acid to water when you are diluting. And so, you know, it could be just a good practice that anytime that you're making a dilution, for example, put a little bit of water inside of your volumetric flask first, and then you know that you're still adding acid to water, so it makes it a little bit safer that way too. Okay, and now we've got names and formulas of acids and bases. Okay. So this is a review. Typically, we've got our hydrogen ion here, and your X could be whatever anion that you have is your X minus. And so remember, naturally there are three endings. There's ide, ite, and ate as our three key endings. If it's ide, we're going to use hydro-ic. If it's ite, we use us, and if it's ate, we use ic. And so I say ide, ite us in the ate-ic. So hide itis in the ate-ic. Everybody say it. Hide itis in the ate-ic. Okay, now, everybody's going to do this with me, okay? Yes, hydro, no polyatomic ion. Okay, everybody do it with me. Yes, hydro, no polyatomic ion, okay? Or no hydro, yes polyatomic ion. No hydro, yes polyatomic ion. So there are two polyatomic ions that end in "ide." So one is hydroxide, which is pretty easy, and the other one is cyanide. Okay, now hydroxide you're not going to name as an acid, and the reason why you're not going to name it as an acid is because it's H plus with OH minus, and when you put H plus and OH minus together, what do you get? Water. And we don't call water an acid or a base, right? Because water would be both acid and base. But the other one, cyanide, you do actually follow these same rules. That's the only polyatomic ion that you're going to use where you're going to begin that with a hydro. So if you had HCN, for example, it would be hydrocyanic acid. Okay? The bases are pretty easy. You're just going to name these the same way that you do ionic compounds. And so you just do whatever the cation is. You name the cation with its positive charge. So it can be any metal, or maybe it's a positive ion like ammonium. And then you name it with hydroxide at the end. If it's an Arrhenius base, then that's how you would end up naming it. Okay, so if you had like sulfur, for example, so we would just have the sulfide ion, we can have the sulfite ion, and we can have the sulfate ion. And in front of each one of those, if you had the hydrogen, well, it would be H plus with an S negative 2. And so, for example, here it would be H2S after you crisscross your charges. So no polyatomic ion, yes, hydro. So this would be called hydrosulfuric acid, okay? And then if you had H plus with SO3, which is called sulfite, then in this case, it would be H2SO3. So sulfite would switch to sulfurous acid. Now, the UR, I always say go to the R in the original name. So it wouldn't be sulfa, so it would be sulfurous acid. Okay, and then the last one that you can have is your H plus with SO4, negative 2. And so again, it's H2SO4, and that's sulfate. So then 8 you would change to ic, and so that would be sulfuric acid. Okay, so let's have you try out the names on the bottom of the page, and we're just going to pause here for just a minute. Okay, and so if you can just check your answers there to make sure that all of your answers are right. Don't forget always to make sure that you crisscross. So double check here. Did you remember to crisscross the 2 from the chromate in chromic acid? Did you remember to crisscross the 2 here in the iron 2 hydroxide right there? We've got our nitrous acid, so that's nitrite, which is NO2. So just making sure that you have some of these down. And just an FYI, this is a hydroiodic acid, which comes from iodine. So that's a D right in there. Okay, we know that when we're talking about IMFs, that water is very something. There's a word that we use about water. We say it's very polar. Awesome. Water is very polar. And the idea of polarity, remember that you can have either you have an ionic bond or you have a covalent bond. And in covalent bonding, the electrons are being shared. But you can have equal sharing, that's non-polar, but if it's polar, then it's unequal sharing. Okay? And so we know that you get your oxygen, which is more electronegative, and then the hydrogens, and you get a dipole, which is pointing toward the oxygens, okay? And then we have our dots, and it ends up being a bent molecule, okay? And so there are collisions between other water molecules because this has a partial negative charge, and this side has a partial positive charge, and so does this side. When it comes in contact with other water molecules, they basically can exchange different ions, which sounds weird, okay? But it can either gain or it can lose the hydrogen ions when that happens. So if a water molecule becomes negatively charged, becomes hydroxide, what happened to it? It lost a hydrogen ion. So if it loses a hydrogen ion, then it'll become hydroxide. Okay, well, this is weird. A water molecule can also gain a hydrogen ion. And if it gains a hydrogen ion, then what does it become? It's not H2O anymore, it's H3O. And this now has a positive charge, and that's called hydronium. Okay? And you're going to need to know this, but what I'm going to tell you is, in textbooks, there are disclaimers, and it'll say, rather than calling it hydronium, we're just going to call it the hydrogen ion. So even though it's actually true that when water self-ionizes, it forms hydroxide and hydronium, the way that we always write it is we just write H plus OH minus, but you do need to know that it's actually the hydronium ion and not the hydrogen ion. Okay? okay? So despite the disclaimer, just make sure that you're aware of that. So two water molecules produce ions, so we can see that the water will dissociate into H plus and OH minus, but again, we're gonna rewrite this, but with the hydronium ion in a second. In pure water, if you're at 25 degrees Celsius, then the concentrations of the hydrogen and the hydroxide ion are equal to each other. And this number is very significant here, this 1 times 10 to the negative 7th. We say that it's neutral. Now, this isn't a nice number to use over and over and over again. It's a very long number, so to say, 2.6 times 10 to the negative 4 or 1.8 times 10 to the negative 3, that takes a lot to be able to write that over and over again. And so we're going to talk about the simplification of these. Instead of using the concentrations, we use, instead of saying concentration of H plus, we use pH. And so to find the pH, we just negative log that number. And so we're going to come back to that in just a second. And so the pH would actually be equal to 7. And the reason why is if you negative log this number, you'll actually get a 7. Okay, so if you hit negative log and you type this number in your calculator, you'll get a 7. So that's the significance of that. So H plus and OH minus are interdependent. When one goes up, the other one goes down. And vice versa. As with Le Chatelier's principle, if you increase the concentration of an ion, the equilibrium always shifts how? In the opposite direction. So if I add hydrogen ion, if I have too much hydrogen ion on the side here of the equation, my hydrogen and my hydroxide are actually going to come together and they're going to form water. And so these will react with each other to form more of the water. In other words, for the reaction, now we are going to write it as H3O plus, but then, and we'll put it in parentheses, okay? So we'll say H plus plus OH minus. If you increase the H plus, then what will you end up favoring? The opposite side, which is the reactants, meaning that you'll end up making more water. Okay. Okay, so what we have here is we've got a fat simulation, and this is showing just water right now, and so we can see that the pH is equal to 7. So we've got two water molecules that's balanced out, and then it gives us the H3O plus and the OH minus. So they're not actually showing the water molecules inside of here, which would be our Mickey Mouse guys. They're not showing those. That would just be in the background here. So we could show the solvent, but I guess you can still see everything else, so that works out too. Now we can see our H3O plus, these are the red guys right here, and then our hydroxide is the blue that's in there. And right now, everything is equal in concentration. So if we had something like a strong acid, we can check to see now the pH just changed to 2, to 2.00. Well, we have a lot more reds in here. What is the red representing? Is called hydronium. Yes, that's called the hydronium ion. And then we can see the blues here are actually representing whatever our base is. And we'll talk about what those are called. So they're conjugates. And so we'll talk about that later on too. So what would it look like if we had a weak acid? Well, if you have a weak acid, then you can still see that the pH is 4.5, so it's a little bit higher. It's closer to 7. But we see that we have these red guys, and yes, we have some of these blues. But as long as one of them is predominating, then you would say that that's still an acid. Here's what our strong base would look like. Now you can see we do have this M plus ion, which it could be any positively charged ion that you have, but now you've got a whole bunch of the hydroxide ion that's inside of there. And that pH jumped to 12, and then a weak base should be closer to what? 8. Closer to 7, yep, maybe closer to 8, something like that. This is at a 9.5, and so again, you can see that there's a little bit more balance. We're closer to being a neutral solution. So just to kind of give you an idea of how those ions would look if you had a strong acid or a strong base solution. Okay. So this equation right here is very, very useful. It allows us to switch between hydrogen ion and hydroxide ion. It's very simple, okay? If you know one, you can always figure out the other one, and all you have to do is, because you only have, once you know one, you only have one unknown, right? And so all you do is you take this number and do what to the one that you know? Divide. That's it. It's that easy, okay? So whatever, if you're looking for the H plus, you do this number divided by your OH minus. Or if you're looking for the OH minus, do this number divided by the H plus, and then you can always figure out one and the other. Okay. So now, and this is pretty easy to use, by the way. So if it is a 1.0, so let's say that my acid, or let's say that the concentration of my substance is equal to 1.0 times 10 to the negative 6. then what would my, let's say that's my hydrogen ion concentration. What would my hydroxide ion concentration be? 1.0 times 10 to the negative 8. Why? Because they have to add up to equal 10 to the negative 14. Awesome. So what if it were 1.0 times 10 to the negative 2? That was, let's say that's my hydroxide. What would my hydrogen ion be? To the negative 12. Awesome. Perfect. Okay, so it's always going to add up to equal negative 14. So you can switch back and forth between them. If your hydrogen ion concentration is more, it's an acid. If your hydroxide concentration is more, then it's a base. Okay? Don't forget, these are 10 to the negative numbers. So if you have 10 to the negative 2 versus 10 to the negative 12, what's bigger? 10 to the negative 2 is going to be bigger. Okay? So your acid solution, the hydrogen ion is greater, and your basic solution, the hydroxide ion concentration is greater. Okay, so if your hydrogen ion is greater than 1 times 10 to the negative 7, we already said this, that's what you would call acidic, and the other way around would be called basic. Okay, so let's see if we can classify these. Now, you could look at this and give me an approximate pH, okay? So in this case here, what is my approximate pH equal to? My pH is approximately equal to what? 10. I like it. Perfect. Because the exponent is the 10. Now, if you negative log this, you're not going to get exactly 10, okay? But because it's to the negative 10, you know it's going to be around a 10. So what would you say that this is, acid or base? Base. Awesome. Okay, so let's pause for a second here. Let's see how you do. Now, the only thing I'm going to tell you before we do this is this would give you the pOH is approximately equal to, in this case, what can you tell me? It is equal to 7. It's going to be neutral. If your pOH is 7, what's your pH? 7. So keep in mind that pH plus pOH would equal 14. So we're going to come to that in just a second here. Okay. So let's see if you can try these out. You don't have to switch it to pH or pOH. I just want you to use the number to be able to tell. Okay, so I want you to check your answers here. I think that probably the trickiest of all of them would be letter B. So on letter C, 10 to the negative 14, that's basic, that's pretty easy. You know your pH is going to be about equal to 14. And this one we already talked about here, that's neutral. This one here, pOH is about 2, so you'd have to subtract from 14, so that gives you a pH about 12, so that's basic. And same thing here, your pOH is about 12, so your pH is about 2. Let's come back to this one here. So 2.0, you know 1.0 times 10 to the negative 7 is exactly neutral. But this is your hydrogen ion, and your hydrogen ion concentration is a little bit more than neutral. If you have more hydrogen ion, that makes it acidic. There we go, okay? So if you check the pH of this, it actually will give you something like a 6.7. So it's still pretty close to neutral, but it's something around like a 6.7. On there. Okay, so we've already talked about the pH concept, but let's do this with the notes. So in 1909, there was a Danish scientist, and yes, his name was Søren Sørensen, who wanted to keep things simple. I mean, I don't know how much more simple you get with your name. And so he proposed the scale using H+, from basically 0 to 14, instead of using the units of molarity, which were, again, like 10 to the negative 3, and 10 to the negative 11, and 10 to the negative 13. And so he calls it pH. And so it's pretty simple. When you see this P, all you're going to do is negative log it, okay? And so this actually is an equation. It is the simplest and smallest form of an equation that we've ever seen. What do you think the H is? It's your H plus concentration. That's it. So all you have to do is negative log your H plus concentration, and that's what your pH is, okay? So this is actually an equation. And so you can go back and forth between, and I'm going to make sure that you know how to switch back and forth, because we're used to, if you know the concentration, can you switch to the pH? But what if you're given the pH and you need to switch out of it? Because that's going to be appropriate and very useful in AP. So we also know this equation right here. The Kw is H plus times OH minus. We already talked about that one. And if that's the case, then if you negative log this, you can also do the negative log of H plus the negative log of OH minus to equal the negative log of this number, which is 14. So that's how this equation matches this equation. Just keep in mind, this one's being added, this one's being multiplied, okay? Or divide if you need to switch between the two. So these are the 4 key equations that you're going to find very useful in this unit. So we've got pH plus pOH is 14. We've got our H plus OH minus. This is what they call the Kw equation. The ion product constant for water is what Kw is. This is the definition of pH, and this is the definition of POH. So again, both of these are very simple equations. If you just see pH, that's negative log H plus, so what must this be? Negative log OH minus. And so there it is. It's a negative log of OH minus, and you can switch between. Okay, so we know for a neutral solution that your H plus is 1 times 10 to the negative 7, and so is your OH minus, and your pH would be 7. If it's less than 7, we already talked about this, it's acidic. The fluids in your stomach should be around I believe it's a 2.2, something like that. pH, and that's actually hydrochloric acid that's inside of your stomach as well. pH greater than 7, household ammonia, has a pH around, I'm going to say 12.6, something like that. Okay, so a couple of calculation tips that we need to make sure that we go over. So if you're calculating the pH, all you're going to do is you're going to hit the negative button in your calculator, you're going to hit the log button, and then whatever your hydrogen ion concentration is. So if they tell you that your hydrogen concentration, like down here, is 1.0 times 10 to the negative 12, all you're going to do is you're going to say that pH is equal to negative log of that number. You're just going to plug that right into your calculator. And what can you see? What would you get here? 12. Okay, but now we're going to write two answers here because we're going to do the pH and the POH. So I'm not going to write 12 though, because writing 12 does not give me any sig figs, okay? So the sig fig rule here is when you're reporting pH, only the numbers after the decimal are significant. So 5.00 only has 2 sig figs. Which numbers are significant? Those two right there, okay? So when you report pH and POH, this is only for pH and pH. If you're doing concentration, it's the same as what we've always done. Then I don't want to leave this as 12 because that's 0 sig figs. Isn't that weird? That's 0 sig figs. Okay. So how do I make that? This is 2 sig figs because that's normal. That's molarity. We've been doing that since the beginning of the year. The only thing that's different is pH and POH. So how would you make this 2 sig figs? 0.00. Now let's do our POH then. That's pretty easy because all we have to do is subtract from 14 and we get 2.00. Okay. So now that's if you're switching from H plus to pH, okay? The same thing, you would do the same thing if you were trying to find the POH. You would do exactly the same thing and then you can subtract from 14 to find the pH. So it just works backwards. Now, if you're given pH and you're trying to find the H plus, this is backwards, okay? So we know the equation is pH is equal to negative log of whatever your number is. And so let's say that the pH is equal to 5, okay? And this is our H plus concentration. Well, if the pH is 5, what am I being given in this equation? Which side am I being given? The left. Oh, so this is weird. This is saying that 5.00 is equal to the negative log of H plus. Now, what do you have to do mathematically? What do you do first to simplify this, to get this so that I'm just solving for H plus? Okay, so you would think divide by the negative log, but those of you that are in upper level math classes, you know that that doesn't work. You don't divide by negative log. What do? Inverse log. Awesome. You have to do inverse log, okay? But inverse log, what about this negative? Move that over first, okay? You actually have to move the negative over first and then inverse log it, okay? So I want you to try this in your calculator, and what you should get is that your H plus concentration, and how many sig figs would 5.00 have, if that's my pH? 2. Remember, only those two count, okay? So that's 2 sig figs. Now, I know it's exact, so I'm going to get 1.0, that is 2 sig figs, that's not pH, times 10, anybody want to guess? To the? Negative 5. Awesome, negative 5. Okay, so that's without a calculator. I know what I should be getting, and that's molarity. So what should my OH minus concentration be if that's my H plus concentration? 1.0 times 10 to the? Good. Negative 9. Perfect. To equal negative 14, right? And so that would be molarity as well. So this would be my H plus concentration. This would be my OH minus concentration, okay? So I want you to try this in your calculator just to make sure. So again, what you're going to do is you're going to hit inverse log, hit the negative button, and then the 5.00 goes in. And that's how you're going to get this answer right here, okay? So let's pause for a minute. Let's make sure that you can get some of these calculations down. These two we don't necessarily need a calculator for. Actually, we can do these pretty quickly. This is 1.0 times 10 to the negative 2. So if that's the case, what's the pH if it's 10 to the negative 2? 2.00. Awesome. And then what would my pOH be? If it's 2.00, it would be 12.00. Perfect. And this is a pH of 7, so what should my concentrations be? 1.0 times 10 to the negative 7 for both of them. Okay? Molarity and 1.0 times 10 to the negative 7, again, molarity. Okay? So let's pause here and let's see if you can work on some of these on the bottom. Okay, so let's have you check your answers. Now, some of these are very strange, okay? So we're going to take a look at some of these together. Now, the first thing that I'm going to tell you is, this we're not used to. Now, we've done problems like this before. So in the past, we've done problems like this, where in Honors Chem, you would be given a particular solution. But the one thing that you need to keep in mind is NaOH is going to break up into Na plus and OH minus. So if you know the concentration of your OH minus, then that means that when you solve for this, you're actually finding POH. So if you just negative log this number, because those are hydroxide ions, then that gives you the POH. So how do you find the pH once you know the POH? Subtract from 14, and so we get 2.75. Wrong. This is right, but it's wrong. If I told you that the hydroxide concentration was this would be fine. That would be perfectly right. That's exactly the answer that I'm looking for. But if this is a base, and all I have inside of there, it's a solution, right? It's a solution of a base. Does it make any sense that this would be acidic and very acidic? No, it doesn't make any sense. When the concentration of the base is so low, like this is here, it's 10 to the negative 12, which is a really, really small amount. If you think about that being in water, that's a really small amount, right? Isn't it mostly water? So guess what the pH is? 7.00. Okay? So what happens is, if your solution, if you look now, if they told you hydroxide or hydrogen ion, you go with it. You do it as usual. It's just normal, okay? But if they actually tell you what the solution is, and it's a base or it's an acid can only be as high as 7. So an acid only has a pH between 0 and 7, and a base has a pH between 7 and 14. Okay? So keep this in mind, because that's going to be a trick, and I will tell you that on the AP, they'll have multiple choice questions. And it'll say, this is the concentration of the sodium hydroxide solution, what's the pH? And people will flip out, because they'll be like, the pH should be about 12. And 12, like something like 11.6 or something like that, like an answer like that is there, but the correct answer would be 7. Okay? So if it's a small enough concentration that it's not going to matter, then it's just water. Okay? So here, same thing, you just negative log it, and you get that the pH is 3.59. Here we negative log it. The only thing is it's hydroxide again, so it'd be 1.00. To find the pH, we subtract from 14. So we get the pH is 13, which would be basic. This is going backwards. So remember, you have to do inverse log the negative 8.3, so 10 to the x. And then you get the 5.0 times 10 to the negative 9 for your H plus. How do you find the OH minus when you know the H plus? There are two ways to do this. So one way that you can do it is using the KW equation. What do? 1 times 10 to the negative 14 divided by your H plus. Okay, so that'll give you your OH minus. And if you already have this in your calculator, I think it's easy enough to just do this divided by answer to figure out this one. Okay. The other thing you could do is you could switch pH to POH and then do what? Inverse log the negative of the number. Okay, so you could do either one, that'll work. And then same thing here. So this is POH, so when you figure out this answer, that's actually your OH minus. And then you can, again, 1 times 10 to the negative 14 to figure this one out. And last one here. What can you tell me about this? Now, they're not just giving us the pH or the POH, or like up here, the H plus or the OH minus. They're actually telling us it's hydrochloric acid. What can you tell me about this? Yes, this is wrong. Again, the highest an acid can be is 7, and the lowest the base can be is 7. Okay, so the pH would actually be 7 in this situation. Okay, so that's it for our introduction to acids and bases, naming, and doing some